Microplastics in the environment is a real problem. It's present in air, water, and soil, but particularly water, where you're most likely to encounter it as a person. So we're going to talk a little bit about how to find microplastics using either Pyrolysis GC-MS or TED-GC-MS. So where would you find them in general? What kinds of samples? What kinds of water samples in particular? It can be found in simple pond water or surface water, household drainage, also known as gray water, street water runoff, very common to find rubber particles this way. Bottled water, unfortunately, it can also be found there. We have all these different kinds of samples to look at, but no matter what kind of sample, we're going to basically use one of two techniques to find what we're looking for. We're either going to be using Pyrolysis GC-MS or TED-GC-MS. For the analytical details about how either one of these work, please come to the GERSTEL website and we can get more information on the particulars. But in general, no matter which technique you use, the overall process is the same. We have to take a sample, we have to prepare the sample, analyze the sample. We get a lot of data out of microplastics, as you'll see later. We need to reduce that data down into something that gives us results quickly. So no matter which way you go about this, your workflow is largely the same. So let's start with sampling first. What does sampling look like for microplastics in water? Well, in either case, it's going to be some kind of filter involved. We're going to take water through a filter. If we're using pyrolysis, we're later going to pyrolyze the samples. So we're going to use a glass fiber filter for this, typically fairly large, 47 millimeters across. And at the bottom here, you can see 4 different examples of what these kind of samples look like. The bottled water example, of course, is very clean, but there are microplastics present there. Obviously, the pond water drain-off is going to be the worst out of all of it, containing a lot of organic matrix in there that we need rid of. But if we're going to pyrolyze, we'll take water through that filter. If we're going to use TED-GC-MS, TED uses these steel cups. The steel cups normally have a solid bottom, but for microplastics and water analysis, we can get versions of this that instead have a stainless steel mesh that gets us particle sizes that are similar to what the glass filter would get. So once we have our sample on a filter, then what do we do next? We have to prepare that sample. So in the case of pyrolysis, this is a pretty big sample, and Pyrolysis GC-MS works best on sample sizes of 100 to 1,000 micrograms. That's because the mass spec is an incredibly sensitive detector, so we need to keep the sample sizes down. That's a lot of sample you see there in that picture. Tens and tens of milligrams of sample there. We've got to cut this down somehow. That's done one of 2 ways. You can use a punch to take little individual punches out of that filter that reduce the sample size down of each punch to around 100 to 1,000 micrograms. That's very effective, cost effective, but does turn one sample into 10 because you're going to have to punch many times to get a representative sample. The other way to do this, which is commonly done in standard methods, is to cryomill that entire sample into a homogeneous powder. If we do that, we get one homogeneous powder that we can then take a representative 100 to 1,000 micrograms out of. Of course, this requires not only a cryomill, but the manual steps of having to run the sample through the cryomill and the cleanup before and after. Alternately, in TED-GC-MS, we're going to take that same sample and run it through, again, one of these cups that has a screen in the bottom. We're going to get similar particle sizes. We can get our 15 to 25 milligrams here. It would be too large for pyrolysis, but it turns out that for TED, that's actually a pretty good size sample. TED can handle much larger samples without saturating the detector. This is great because now the sample is more representative and your sample prep is done here. Run the water through a filter, and that's all, or through a TED cup, and that's it, and you're done and over with. So once we have our sample, now we need to analyze it. And again, that comes down to either using Pyrolysis GC-MS. In pyrolysis, the process is going to be compliant with ISO standards. There's also an ASTM standard using pyrolysis on this, by the way. Pyrolysis is simple. The actual analysis is fully automated, even though the sample prep is not. There's a complete microplastic workflow available from GERSTEL that's very reliable and flexible for processing all these samples using pyrolysis. Alternately, using the TED technique, it's also compliant with ISO standards. It's also fully automated and right away gives you representative sample sizes because the samples when you took them to begin with were already larger and representative, requiring no additional work. There's also a complete microplastic workflow available from GERSTEL involving minimal sample prep, and of course is also very reliable. So now that we have our data, we need to get from the analysis from that data to a result. How do we do that? The answer is we're going to use GERSTEL's ChromIdent software Pyro bundle to do this. It's the same bundle that's used for either TED or GC-MS. It starts with having a library. There's only around 16 to 20 or 24 or so common microplastics in the environment. Not hard. We have a library, not hard to create your own. The number of samples is pretty limited to do that. But once we have a library, we're going to process our data against that library, looking for marker peaks. For styrene, there's typically for polystyrene, there's typically 3 marker peaks. For polyethylene, there's dozens of marker peaks. One way or the other, we're going to look for those marker peaks, and we're going to match the sample against these marker peaks, looking to identify it. One of the things ChromIdent really does really well is that when it identifies positively the polymer is present, you get a little green barcode, as you can see there in the window on the right. You can visually tell which microplastics are present really quite easily when we get a positive identification through ChromIdent. Once we have those polymers identified, then we can take those peak areas and quantify those polymers as we normally do in chromatography and get to a final result. So as an example of how this whole process works, let's talk about facial scrubs for a minute. Now, facial scrubs are not water, clearly. So why do I worry about microplastics in facial scrubs? Well, simply when you're done scrubbing your face, you're going to rinse it off and it becomes part of that household drainage or gray water. So microplastics get in this way, and it's been documented in research papers that this does indeed happen. If you look at a rinsate or gray sample after a gray water sample after a facial scrub's been used, you'll get this kind of data. This was done by Pyrolysis GC-MS, pretty complicated, complex data analysis. Fortunately, ChromIdent will go through there and hunt out all the microplastics that are present and identify them and quantify them for you. So you can handle all of this, but maybe you want some more information out of this than just the polymers. Maybe you want to see more. There's an interesting way to do that. And this is called fractionated, or in this particular case, because we did it 3 times, triple shot pyrolysis. Instead of normally in pyrolysis where we heat everything to 600 degrees as quickly as possible, we're going to take one sample and instead heat it 3 different times at 3 different temperatures. First, relatively low, we get the volatile components. Here you see some of the acids that are present, the fatty acids that are present in the soap that's in the facial scrub. Next, we're going to heat it higher to get the semi-volatiles out of it. The amide that you see there is one of the detergents that's in the facial scrub. Then we finally heat it to pyrolysis temperature to 600 degrees. In this case, if you look at a lot of these pyrograms all day like I do, that particular peak pattern that occurs in triplicates with the ane, ene, and diene in it pretty much tells you right away you've got polyethylene in there. So this facial scrub does have polyethylene microplastics present in it. So this provides simplified chromatograms if you do it this way, and simplified data interpretation. Again, you can use ChromIdent on each different file and identify the different components, either microplastics or surfactants or whatever else is present there. It works for all of these things. If you want more information, take a look at GERSTEL App Note 212, available on the GERSTEL website. So one way or the other, whether you use the Pyrolysis GC-MS or TED-GC-MS, GERSTEL makes microplastic analysis work. Please come see us, get some more information on our website about how we do all this work. We really hope you enjoyed this video and all the others in this series, and please stay curious.